Hi guys, in this video we're going to talk about macroscale fractional distillation and gas chromatography lab. Before continue to watch this video, please go ahead read the textbook. The page numbers are given in the lab manual as well. Please go ahead, read thoroughly as much as you can and try to understand all the background and concept behind this experiment. Okay, so there are two sections that you need to watch. One is experiment 7, page 56 to 63, and then technique 22, which is describing about the gas chromatography, pages 829 to 848. Now, after reading those textbook assignment, now I'm going to just briefly explain about today's experiment, which is distillation first. So basically, distillation is a technique used to separate and purify a liquid component from a mixture. And this liquid mixture is heated. Basically, we're just heating that mixture to its boiling point. So once the liquid boils, then its physical state changes from the liquid to vapor. But then these vapors escape from the apparatus, and eventually, once they reach the cold area in the apparatus setup, then they will eventually condense, and we're going to collect those condensates. And that's basically how the distillation works. We just boil the liquid mixture, and based on their boiling point, we can separate them. So in this experiment, we're going to separate hexane and toluene. And basically, hexane has boiling point of 69 degrees in Celsius, but toluene is 110 degrees in Celsius. So by using this about 40-degree difference in the boiling point, we're going to separate them. Okay, and after separating these two components, we're going to analyze and evaluate this distillation method by using gas chromatography. Let's talk about the basic fractional distillation setup here. This figure is from the textbook, and actually this figure displays the microscale fractional distillation apparatus, but the macroscale is not much different. They're just bigger glasswares. And if you watch the experiment video, you can also see the macroscale glasswares, and they are basically the same glasswares, but different sizes. So we're going to place the liquid mixture, which is hexane and toluene, into this round bottom flask, and then on top of it, we're going to place this fractionating column. This fractionating column is very important, and that's what this fractional distillation is different from the simple distillation. Without this fractionating column, it will be just simple distillation. But by having this one extra piece of equipment, is going to make our distillation more accurate and precise. So normally in this fractionating column, there are stainless steel sponges filled inside, and then on top of it we have thermometer adapter here, and then distillation adapter, and then thermometer adapter goes on top of it. That's where the thermometer is placed and holding it. Then from this distillation adapter, we're connecting this water cooling condenser. Okay, and then the last glassware is going to be a vacuum takeoff adapter to collect or to provide the distillate to fall down to our collector, which is 10 milliliter graduated cylinder. So now in this water cooling condenser, the water goes in, and then the water is running inside the condenser, and then the water comes out. Okay. Sometimes the students ask how this is possible. Well, because it's a double wall. The water is only running the outside of the actual the inner part. So once the vapor escapes from the fractionating column, they will eventually get into this condenser, and since cold water is running, then these vapors will condense, and its physical state changes from gas to liquid, and that's where the liquid comes down and we can collect them. Okay. So the most important part in this fractional distillation is this fractionating column, as I mentioned earlier. So what it happens is we're going to hit this mixture on a heating mantle, or sometimes on a hot plate, or sometimes on a oil bath. Then the liquid is going to start evaporating. It's going to start boiling. Then the vapors of the first component, let's say in this experiment we have hexane and toluene. Hexane has boiling point of about 69. So this hexane will eventually start boiling first. Then it will saturate this fractionating column with the hexane vapors. But at the same time, a little amount of the toluene is going to also start boiling, and sometimes the toluene molecules are carried into the fractionating column as well. So the vapors are filling up this fractionating column, but at the same time, this fractionating column is cold at the beginning. But once the vapors are filling it up, then these vapors will start the condensate. So in the meantime, in this fractionating column, these vapors will undergo multiple cycles of evaporation and condensation. So if you look carefully during the lab, if you're in person, if you're taking hybrid lab, then you will see there will be like a vapor ring forms at the beginning, but then it will slowly go up. Then what's happening here is that the more volatile component, which is hexane, will eventually go higher, but at the same time, the less volatile component, toluene, is going to actually stay the lower side of the fractionating column. So toluene will stay low, the hexane will stay on the high side in the fractionating column. And that's where the first separation occurs from the mixture. Okay. And then this vaporized hexane will escape this fractionating column, get into the distillation adapter, then the vapors get into this condenser, and they hit the cold wall, and they condensate. And that's where we get the drops of the first component into the collector, which is graduated cylinder. So basically, we're just boiling the liquid mixture, and depending on their volatility, we can separate them. Okay, so physical state changes from liquid to the vapor, and it comes back to the liquid at the end. So in this experiment, there's one thing you need to record, which is the distillation temperature and the total volume of distillate. If you're taking this course as online, then you will just use the table with the temperatures like provided in the report template. But if you're taking this course as a hybrid group, then you have to fill out this the temperatures. You have to, make an observation and just keep recording this distillation temperature for every 1 milliliter of the fractions. So if you get 1 milliliter of the distillate in your the collector, then you have to record the temperature from the thermometer here. Okay, and after completing this table, now you have to draw the distillation curve. I assume you guys have learned how to draw a graph using the Microsoft Excel. So from the table here, you can just put all these numbers and make one nice distillation curve, and you have to include this in your lab report. So lab report template provides some basic guideline what's expected in the report. So for the fractional distillation, if you drew the right graph, then the shape of the graph will look like something like this. Okay. This example here, the blue curve, is actually simple distillation curve, which we don't do it in 347. I mean, we used to do it before pandemic, but now we're just doing fractional distillation. Okay. So you have to complete this distillation curve for the report. Okay, let's talk about gas chromatography. So after completing the distillation, let's say we successfully separated hexane and toluene from the mixture by distillation. Then we have to analyze how well this distillation worked. So we're going to use this gas chromatography. This is an instrument that separates the components of a mixture or from the sample based on their boiling point. So the principle is a little bit like similar to the distillation. If we have lower boiling component in the sample, it will actually pass through the column first, and if it passes through the column more quickly, then it will have like shorter retention time, not less, shorter. Okay, so you probably have no idea what I'm talking about here, but if you already read the textbook, you probably have some idea what's going on. So let's take a look at the basic schematic diagram of a gas chromatograph. So it's an instrument, it's a machine that has multiple components. Okay. First, it has the injection port, and then it has let's say the body of the system, which is called the oven, and we actually call it as a stationary phase. Okay, and then the last part is going to be our detector. That's where what component is escaping from the stationary phase. That's what we detect. So let's take a look at from the beginning. We have a through the injection port, we only apply about 1 microliter of the sample. It's really tiny amount. Okay, so by using a syringe, we're going to inject our first fraction 1, which is the distilled first from the hexane toluene mixture. And once we inject it, what's going to happen is the temperature inside this injection port, it's very hot. The temperature is high. It's about 250 degrees. But we know the hexane's boiling point is about 69 degrees, which means as soon as the sample is injected, then this liquid, the hexane, is going to vaporize and it will stay as a gas molecule in the injection port. And right after that, we have a gas called carrier gas. Normally in this GC instrument, helium is used as a carrier gas. So what it does is this helium gas is going to carry these vaporized hexane, the fraction 1 components, into the oven. And in the oven, I said this is a stationary phase. So in the oven, we have a coil, which is called a column. So on the right side, this is a general picture of the column. This is basically the capillaries that, the inner part, the inside of the capillary is coated with some non-polar materials inside. Then what's happening here is these vapors, once they get into the column, then by applying the pressure from the carrier gas, it will go through the column. And normally this column is about 20 to 30 meters long, or sometimes up to 50 meters long. It's really long, thin capillaries. So once these vapors go through it, then that's where the separation occurs. Let's say if you have multiple components in your sample, then they will be separated in this long capillary based on their boiling point. So when the first component, which is the most volatile component, passes through the column first, then they will reach to the detector first. The detector we have here is called FID detector. I mean, you don't really have to know, but it's called the flame ionization detector. There's a flame that ionizes all the components, and that's where the detector is catching signals to the computer. And we will end up obtaining a chromatogram. Okay, so the most important concept you want to know about the gas chromatography is that this carrier gas is called mobile phase. Okay, the mobile means it's moving. So mobile phase, the carrier gas, is carrying the components, and then in the stationary phase, that is where the actual separation occurs. So mobile phase and stationary phase are the most important the concept that you need to remember even for the final exam. Okay, so now let's take a look at chromatograms, how those are signals we can see on a computer. So in the chromatogram, basically we're going to see a graph, and the x-axis is labeled as a minute, so time, and y-axis is just it's a relative intensity. So let's say we have hexanes in fraction 1. Fraction 1 is supposed to be only hexane because it has a lower boiling point, and we separated hexane from the mixture by distillation. So we're expecting to see just one signal for the hexane. Okay. However, if you have more than one component, let's say the distillation didn't work very well, then you will see the multiple signals in your sample. So it really depends on the purity of the sample you're running or you're checking. If it's pure enough, almost 99%, then you will only see one peak. But if it's not pure enough, then it will show even 2-3%, 1-3% of the impurities here. Okay. Now the problem is, although we're expecting to see only one signal for our hexane, but the hexane stock solvent we're using is actually called hexanes. It's plural, which means in this stock bottle we have many hexanes. So hope you guys remember about the constitutional isomers. So hexanes means we have about 50-60% of N-hexane in this bottle, which is just straight chain of hexane. But the rest of about 40% of the stock bottle, the sample in the stock bottle, they have constitutional isomers. And constitutional isomers are the isomers that have the same molecular formula, but they have different connectivity. The reason we're using hexanes instead of the N-hexane is this N-hexane is very, very expensive and we cannot afford it. But instead we're using hexanes, the plural, the hexanes bottle. And we expect about 50-60% of N-hexane. The other rest of it, 40%, is going to be the constitutional isomers of hexane. So which means it has the same molecular formula. Could be 5-member, 1, 2, 3, 4, 5. It could be 3-methylpentane, or it could be 2-methylpentane. So all hydrocarbons with the C6H14 is possible for this hexane stock bottle. And technically in the chromatogram, we are going to expect to see 4 peaks. 1, 2, 3, 4. So I assume this number 3 peak is going to be our N-hexane. However, we're going to consider all these components as our hexane. Okay, so let's say we obtained a chromatogram for the fraction 1, and now we need to analyze it. Well, how we're going to analyze it? The textbook and also the old method is using the triangulation. The software, in modern GC instruments, the software has their own calculation method, and they just automatically calculate all the areas and provides the percent composition of the components in the sample. But for the education purpose, we're going to just use the old school method, which is triangulation. So basically what we do here is we're going to measure the height of each peak from the baseline. Okay, remember, this is our baseline of the signal, not the x-axis. So there should be x-axis going on here, and then y-axis here, and you just want to measure the height of the peak from the baseline to the top of the peak. Okay, physically you can just measure it using your ruler. That means there will be 2 chromatograms provided in Canvas in PDF file form, you should just print them out. Okay, so print them out and use your ruler and just physically measure in millimeters for the height of the peak, and also measure out the width of the peak at the half height. Okay, in millimeter too. And then you're gonna just going to multiply these two numbers to get the area of the first peak. So here's the example that the area peak A is 17 times 40 gives you 680 millimeter square, and then for the peak B, the height is measured from the baseline to the top of the peak, and then width at the half height, which is 19 times 122, gives you 2320. And then the total area is 3000. In order to find the percent composition, all you have to do is divide the area of the peak by the total area, and times 100 gives you 22.7% for the peak A, and then 77.3% for the peak B. That gives you the total 100%. Okay, so in the chromatogram that provided for the fraction 1, you will expect to see these 4 peaks for the hexane, and these are all, we're going to just consider these as a hexane. So you probably want to add up all these numbers. Alright, and as well as this fraction B. If you see multiple peaks, still, I mean, you won't be able to see multiple peaks in the fraction 2, but if you see it, just measure and calculate the area of each peak and find the percent composition. Alright, so that's the triangulation that we're going to use to analyze the GC chromatograms. So for the lab report, as I mentioned earlier, you have to print the fraction 1 and 2 chromatograms from the canvas, and then complete your lab report. Don't forget to attach or copy and paste your distillation curve as well, and basically just follow the guideline in the report template. And most importantly, this is the individual work, and you should not show your calculated numbers to anyone. So sometimes, I mean, your measurements are all different. Like, how you print them out is going to be different. So we don't expect to see like exactly the same numbers, like calculated numbers or the measurements from you guys. I mean, everyone is going to have like somewhat similar numbers, but it will be different. And last semester, we actually ran into several students that they just copied to each other all the numbers, and they actually got in trouble. So please don't share your work with anyone, with your classmate, or even your siblings are taking the same course. Still, just do it on your own. And lastly, answer all post-lab questions for full credit. All right. So I hope this helps you understanding our distillation lab. And if you have any questions, please contact me or your lab instructor. All right. Thanks for watching.